So, we have been discussing about quantitative analysis using XPS. Quantitative analysis is very popular in XPS in the sense that we can obtain very high quality informations. And I have already discussed to you about the way quantitative analysis is done. Basically, when you have multiple elements on the surface layer of a material, and if these elements can be represented by I, j and k, then I can write down the ratio of Ni divided by Ni plus Nj plus Nk is equal to this expression which I have written here. Basically, it's, if you look at it properly, it is a ratio of I divided by sigma lambda for the specific element divided by the ratio of the same or addition of the ratios of all the elements, and by this way we can measure the basically the particular element concentration in the surface layer. So, what is needed to be measured is the intensity, and I have already told you how intensities are to be measured using very nice approach. Well, let us see some of the examples. I am going to show you the examples of oxygen metal atomic ratios determined from the corresponding intensities. If you take magnesium oxide, first case MgO, so it is a pelletized powder. The ratio between oxygen 2s peak divided by oxygen metal 2p peak is the concentration is almost 0.95 plus minus 1. As you know, 10% is the approximate error in case of these quantifications, and obviously oxygen 1s divided by metal 2s or magnesium 2s is basically almost like 1.1 plus minus 0.1. Similarly, oxygen 1s divided by metal 2p is 1 plus minus 0.1, and we can keep on doing this for aluminum oxide, Al2O3 thin film, silicon dioxide, Fe2O3, Cu2O, jet oxide, molybdenum trioxide and cadmium oxides. And these ratios are actually average of 6 measurements, and these ratios are very reliable. So, one can actually obtain from the ratios exact oxygen to metal amount ratios for the particular oxide. If you compare this XPS measured quantities with respect to the electron microprobe, things will be much clearer to you. Let us talk about silicon, and this is silicon 2p, so that means it is basically silicon dioxide. So, XPS gives you 27.3 percentage, while that electron microprobe gives you 29.3, just differ by 2 atom percentage. In different wavelengths, this is aluminum, lab, different kind of categories. So, as you can see the values, they are very close by, not differing much. Similarly, for calcium, potassium, sodium, aluminum, and if you look at some of the percentage of the difference is 9% here, is about 11% there, its maximum is actually 11.5 percentage. So, that means XPS gives you reasonably good data in terms of compositions. Although electron microprobe is better, but electron microprobe uses of electron microprobe is not easy if the sample is not prepared properly, and also electron microprobe analysis requires standards which is not required for XPS. So, that is why XPS is easier, but cost of the instrument for the XPS is much higher than the electron probe. So, that is the advantage. Let us talk about errors. As I said, error is approximately 10%. So, II basically the error comes from the intensity measurements. So, what is the problem there? It is basically difficult to separate intrinsic photoelectrons for the extrinsic scattered photoelectrons which comprise the background. That means there are extrinsic photoelectrons which forms the background of the XPS intensity buses, this binding energy peak. So, that means there is a background, and so this background basically comes from the extrinsic photoelectrons, whether the intensity, the peak comes from intrinsic photoelectron. The basic problem is to differentiate between them. That means basic problem lies in fitting the background properly. because the intensity calculation will depend upon how you remove the background, and that is why actually error creeps in, and this error can be approximated to be about plus minus 5%, 5 to 10%. Second important can be coming from the sigma I, which is normally calculated from this plot which I have shown you, and that's the, and there it is basically error of magnitude is unknown most of the cases. Lastly, error can come from the lambda I, estimated error, and then I have already shown you how lambda I is calculated. Let me go back. Yeah, this is how the lambda I are calculated. This is the master plot, a universal curve, and obviously measuring this lambda I, if there is a small error, and then it can lead to error in calculation of the compositions. But most importantly, this is you need to take care very well, otherwise error can be high. Sigma I is normally error is unknown magnitude, so we cannot really predict. Lambda I can be calculated very precisely, estimated very precisely, so there is no problem there. Well, after giving you some idea about the quantification, let me just talk about some other very important issues of XPS. Most important one is obviously chemical shift in XPS. That is why this particular technique is famous for. Chemical shift means the chemical change of the electronic state or the chemical state you can define when some metal is reacting with some oxygen, nitrogen or whatever other elements together. Then obviously we can also find out when some reaction is going on whether initial state and final state. And we also need to discuss about Kuhlmann's theorem, which is very good in analyzing this chemical shift, and we can calculate actually this chemical shift using formula. Finally, obviously one needs to know the line width and resolution for a particular XPS instruments. So let me first discuss about chemical shift, which is very important from the XPS point of view. What is a chemical shift actually? Chemical shift means change in the binding energy of a core electron of any element due to change in the chemical bonding of that element. That means when there is a bonding between two elements, there is going to be change of the binding energies of the core electrons, and this leads to shifting of the peak position in the XPS spectrum. I hope this is clear. I will make it clear by giving some examples also. What is the qualitative view of this? Qualitative view of these core binding energies are normally determined by what? Electrostatic interaction or Coulombic interaction between the electrons and the nucleus. As you know, the nucleus is a positively charged species, electrons are negatively charged species. So there is an Coulombic interaction between these two. So this interaction is what is basically leading to the core binding energies. Now this can be affected or reduced rather by two things. One, the electrostatic shielding of the nucleus charge from other electrons present in the atom, that we know. If there are other electrons present in the atoms, that can act as shielding barrier between the core electron and the nucleus. Secondly, that is the first factor, and that is a predominant factor. Second factor is the removal or addition of the electronic charge as a result of change in the bonding, that will also alter the shielding actually. So that means first one is the shielding of the nuclear charge, second one is the removal or addition of the electronic charge because of the bonding. That can also alter the shielding. Yes, as an extra electron comes, that can alter the shielding. So these two actually are the core binding energies actually dependent on these two factors. So whenever we add an electron or remove an electron from the core shells of the atom, there is going to be change of the charge or change of the binding energies. So that means if you have withdrawal of electronic charge, there is an increase in the binding energy, and this is also obviously known as oxidation. If you take out some electron out of a species, it is called oxidation, and if you add a valence electron charge into it, it is basically lead to decrease in binding energy. This is nothing but reduction. Okay, this is basically can be thought in this way. Suppose you take a sodium and a chlorine. We know the sodium and chlorine reacts and forms sodium chloride, which is a common salt. Now, how the reaction happens you know very well. Sodium actually gives away one electron from the outer shell, and this same electron is accepted by the chlorine. In this process sodium become plus charge and chlorine become negative charge, and then these two oppositely charged species get attracted because of a Coulombic interaction and forms a bond. In this process both the binding energy of sodium and all the binding energy of the binding energy of electron of sodium and binding energy of the electron with chlorine gets affected, and because of these issues we are going to see a chemical shift. I hope I have made you understand clear. Now let me give an example in that way. Let us talk about metal and oxide. You know, we are talking about materials engineering, so it is better to talk about metal and oxide. Let us talk about the simplest possible metal, which is the lithium. We have 3 electrons in its outer shell. There are 2 electrons in the 1s orbit, and that is 1s2, and 1 electrons in the 2s orbit. So basically 1s2 2s1. Now that means what? If we look at the electron density, the 1s2 there are 2 electrons, then 3 electrons. So if I basically have a plot of intensity versus binding energy, we will see this peak for lithium 1s, right. Now what happens when lithium gets oxidized? Lithium gets oxidized, it forms Li2O. That means 2 electrons comes from the 2 lithium charges, or 2 lithium atom actually gives a 1 electron each to the oxygen atom. So the oxygen becomes doubly negatively charged, and 2 lithium ions become singly positively charged, and that is how actually these 2 opposite charge attracted and forms a compound. Now what is the structure of Li2O? Core shell has 1s2, then 2s2, then 2s6. Okay. So 2s6 basically for the oxygen, as you know, there is no 6 electrons in the 2s, but because you have added 2 electrons in the oxygen, so there are oxygen has 4 electrons in the 2 electrons in the outer shell. So 4 electrons, 4 plus 2 becomes 6. So that leads to change in the binding energy of the core electron of the lithium. So that means lithium binding energies gets shifted to the left side, and we start seeing lowering of the binding energies, and this is due to its increased thinning of the nucleus by 2s conduction electrons. The binding energy is higher because Li2s electron density is lost to the oxygen, because basically binding energy increases this way, increases this way, this is the Fermi surface energy. So binding energy is basically higher because Li2s electrons, 2s electrons are here, there is only one 2s electron, there are 1s2 electrons level and 1 electron in 2s level. So because these 2s single electrons density is lost, so there is a change in the shielding of the electrons, and this leads to change in the binding energies, correct. So this can be taught in little bit different way. You know, the photon emission actually can be thought of consisting of 3 steps. First is the photon absorption, that means X-ray photon comes, it get absorbed, then this leads to ionization, that means when it get absorbed and the electron gets ejected, it leads to ionization. This is called initial state effects. Second thing is response of the atoms in the creation of the photoelectron, that means ionization has happened, how electron has got removed, that is why ionization happened, and this leads to in creation of photoelectron. Understand, the photoelectron comes out with a certain kinetic energy. Now third step can be thought of transport of these photoelectrons into surface, and this is what is in extensing effect. This does not depend on the particular atomic pieces, it depends on the surface layer thickness and many other aspects. So first is this absorption, X-ray photon get absorbed h nu, and this is causes ionization of the material. Ionization means removal of the electron from the outer shell or from the core shell rather, and this leads to, in the second step, the photoelectron generation, and then photoelectron moves. So therefore, final state is one additional positive negative positive charge. Initial state you have B A B, and then you have a positive charge attached because of this ionization effect. Usually chemical shifts are thought of as initial state effects. Initial state means ionization, as you see here, it is initial state effect. State effects, relaxations basically is nothing but relaxation process similar to any other relaxation process. In this case, I do not know whether you can see, this is a titanium, this is titanium dioxide. Titanium has 2p 3 by 1 by 2, this is 2p 1 by 2, and this is comes around 460 by electron per binding energy, and this is 2p 3 by 2, this is basically spin orbital splitting of the 2 peaks, and this comes around 453. So difference between these two is actually 675, 67.5, something like that. So the chemical shift for Ti and Ti4, basically charge withdrawn when there is a Ti from TiO2. Well, yeah, let us see what happens in the when this is, I am sorry, this is 6.75. So this is 6.75 electron volt. Now if I form a TiO2, basically I have a change in the electronic state of titanium from Ti0 to Ti4 plus. So the Ti2p half, this is 2p half, and this is Ti2p 3 by 2. You see the distance between these two has reduced to 5.7 electron volt. So that means binding energies or the spin orbital splitting of these two p levels, p2 and half and p2 3 and half, has reduced. So the spin orbital splitting approximately conforming is like I said, chemical information very powerful tool for functional group and oxidation states. So this is basically can be thought of a relaxation process, which is basically due to ionization of the initial state. Now let us talk about what is the Koopman's theorem after knowing what is the chemical shift. Koopman's theorem says the binding energy of an electron is simply the difference between the initial state and the final state. That means what is the initial state? Initial state is the atom with n electrons, and final state is atoms with n minus 1 electron, or maybe more than 1, who knows, that is n minus 1 electrons, ions, and plus free electrons. So that means in the initial state you have fully all the electrons are present in the whatever electron is defined by the atomic number of the element present in the cell, and in the final state you have removed the electron because of the charging, because of the ionization effect. So you have n minus 1 electron, let us suppose 1 electron has got removed, and this extra electron will come as a free photoelectron. So what is the binding energy change? Binding energy is basically n E final n minus 1 divided by initial n. That is what is basically the equation which is used by Koopman's. So if no relaxation followed photoemission, there is no relaxation, so binding is nothing but orbital energy, which can be calculated from Hartrich-Fock theory, which is available. Basically this is a plot of that. This relaxation is nothing but electronic rearrangement following the photoemissions. Please do not get confused with relaxation with surface atoms. Now if I plot experimental binding energies with the calculated binding energies like this, if you look at carefully this chart, they fall on a straight line almost passing to the origin. So these are CH4, CH22H6, C2H4, different kinds of organic compounds up to CF4. So one can actually see the experimental binding energies and the calculated binding energies, they are same. So that means Koopman's theory predicts what is to be estimated or calculated based on this theory and then measure. So this is true. So please try to remember this equation. When there is ionization, this is how we can calculate. Here we have not considered that free electron. We thought this has not any effect because of the relaxation. These are the some of the different values, typical chemical C1s values, and these are taken from those books. As you see here, for hydrocarbon, that is CH or CC bonds, okay, its binding energy is 285, amines this C nitrogen 286, alcohols has COH or COC both possible 286.5 electron volts, fluorine to carbon is very important 286.7.8, carbonates has basically C ON COO 89.6, our CF3 3 bond 3 full atom bond to carbon is 293 to 294. That is, this is a very generic table which is available in the literature. Most values are actually plus minus 0.2 electron volt, that is why this measurement says. For case of oxygen, binding energy is basically up to look at carbonyl group COO or COO 532, alcohol ether C532, ester 533. So, one can actually measure this kind of binding energies using XPS. Well, we can actually explain this chemical shift. As I said, chemical shift is very important using charge sphere model. It is not very difficult to do. For a single atom, suppose which has certain number of electrons, the electrostatic potential is basically given by Coulomb's law QB. QB is the number of Q charges into electron square divided by RV. RV is the distance average radius of valence of electrons. QB is the number of electrons and RV is the electrons. So, change in the binding energies is obviously change in the average number of valence electrons. It's nothing, no effect of these two, they do not get changed. So, if I add the change in the interatomic potential because of this change in the binding energies, then EB becomes Bj minus, and then this is the plus quantity delta QB square RV as you see here. So, Bj is the potential of the atom I on J. That means when suppose Na and Cl. So, if Na gets one electron removed, so because of that there is a change in the binding energy. Now, when this Na plus charge and this electron is taken by chlorine, it comes close to chlorine, there is a potential change. So, one needs to basically use this delta Vij along with the change in the binding energies to calculate the exact binding energy of this sodium ion in neighborhood of the chlorine ion. That is what actually is calculated to in this model, charge pair model. Now, to give you some more examples of chemical shifts, that is what make your understanding clear. Let us suppose carbon 1s in this compound CO, I do not exactly remember this is a 3 fluorine groups, 1 carbonyl group, and then there are CH bonds. So, carbon 1s, if you look at it, this is the typical spin orbital splitting, and these are the two, this S and 2p I think. So, carbon 1s peak actually has this kind of shapes. Now, if I look at the silicon, silicon as pure silicon is here. So, as you see this is close to almost 0, then silicon F, SiF, SiF2, SiF3, SiF4. So, as you keep on having more and more fluorine ions attached to silicon from 1 to 4, the chemical shifts it increases. So, by this way actually one can determine what is the exact state of the atom. So, if I plot the oxidation state versus core electron shift, silicon has no oxidation state 0, silicon F1 has 1 oxidation state correspond to 1 core electron shift, SiF2 2, SiF3 3, SiF4 is little bit higher than 4. So, that means there is a linear relationship between oxidation state and the core level electrons. Second example I am giving you metallic oxygen, metallic iron with Fe2O3 hematite. What you are showing is Ap 2 1 by half, 2p 1 by half. As you see, metallic iron has binding energies of around 707, whereas iron oxide has a broad peak like this and binding energies of the peak is about 711. So, that means there is a change in there is a shift towards higher energies, as we have told already, for metallic iron to the iron oxide. Let us see another example. So, in order to give you Fe2O3, and Fe2O3 is basically what? Fe is 3 state plus 3 and O is oxygen is plus minus 2. So, if I look at this is what is Fe, this is Fe3, Fe2 will come somewhere here, you can see the small peak. Fe2 comes actually in FeO oxide, iron oxide. So, that means we can actually clearly say there is no plus 2 states, all the oxygens are actually plus, the iron is actually plus 3 state. Let us talk about oxygen, in case of oxides and surface hydration. If a metal oxide, this is oxygen S half. So, if you look at oxygen 1 S half, if you look at this is the metal oxide, I do not remember what is the metal oxide, but if the hydration happens on the surface, it is not oxidation, but surface hydration, the peak will come very close by. This is 530.5, this is 532 binding energies. That also can be separated out in XPS. In case of cubic boron nitride, which is a very hard material which is used, let us see what happens when you do the spectrum. Before the iron sputtering and after iron sputtering, we will show both. Boron 1 is peaks, you see this is Bn, this is oxide. Before sputtering there will be some oxides, obviously boron oxide, but if you sputter you clearly see only nitride peak. That is why basically sputtering is used. Now, if you do not sputter nitrogen peak, what happens? Nitrogen 1 is, this is Bn, this is oxide. So, we do not know, this is not a boron nitrogen oxide, this is basically boron oxide B2O3 or something. If you do the sputtering, you have to see only the nitrogen peak corresponding to Bn. So, that means this is very clear, the shift of the compound of the chemical shift of the boron and nitrogen 1s peak positions also function of even oxygen presence on the surface. So, that can lead to some oxide formation. Arsenopyrite, another example. If you look at arsenopyrite, you have suppose arsenic iron sulfide, this is what is called arsenopyrite. So, this can be fitted actually, this is done with 100 micron diameter excess spot, and then we have also showing you arsenic oxide, 2 oxygen state, arsenic 2O3 and arsenic 2O5. Here you see the 2 peaks, one is corresponding to arsenic, other is corresponding to iron, and this is arsenic 3D actually, not arsenic, yeah. So, you have basically splitting, and this is distinctly different from these two. So, arsenic O2, O2O3. So, that means in this sample actually you have both arsenic sulfide, arsenic iron sulfide, as well as arsenic oxide O3, O2 as AS2O3, both are there present. Now, to in a nutshell, after giving you all the examples, I just want to show you some chart where this can be categorically told. This is basically 4F7/2 binding energies of gold and some gold compounds shown from top to bottom. Gold actually has a binding energies of 84. If you have gold tin compound equiatomic, it increases 84.5. Gold tin another compound SN4 85. Yttrium gold, what happens? Ytterbium gold AU2 again sits very close to AUSN. Chloroorophosphoric acid, phosphoric, this basically comes here 85.5. This is again same thing, but 3 ions, there is no change in the positions as you see. Phosphoric acid, phosphine group actually oronitrite, this comes same place, sorry this one decreases here, these two are same, 3 oxides change. So, phosphine group does not change the electronic binding energies of 4F7/2, but if you change taurine 3 in the phosphine group remaining same, it gets increased to 87.5. Chloroorophosphine 3As arsenic decreases. Similarly, iron complex compounds also change. So, that means the 4F7/2 binding energies can be used as a marker to determine what kind of gold compounds are prepared or present in the sample, that is very clear. One can actually use this technique to measure even oxide thickness, it is possible. Let us see what happens for aluminum. Aluminum has always some aluminum oxide on the surface, you cannot remove it. So, if you look at Al2p peaks, there will be obviously this is aluminum metal and this aluminum oxide. When the oxide thickness is about 3.7, high resolution spectrum of aluminum surface, the aluminum metal oxide peak shown can be used to determine the oxide thickness. How it is to be done? Let us see. Usually the binding ends of oxide and the metallic pieces are separated by few electron volts. Thus, when the oxide is very thin, less than about 9 nanometers, it is possible to distinguish the contributions actually from both the oxide and the metal photoelectrons, if it is less thick. For aluminum, oxide thickness is normally given by 2.8 log of 1.4 I0 by m plus 1. This I0s, Ims are intensities of the peaks of oxide and metal position. That means D is for aluminum is given by this formula ln 1 by 1.4 I0 by Im into a plus 1, that is how actually used. So, I0 is basically intensity of the oxide peak and Im is the intensity of the metal peak. So, that means if I know intensities these two or the oxide and metal peaks, I can put in here and find out the basically the thickness, and this is only possible when the thickness is less than 9 nanometers. If it is more than that, then it may not be possible to distinguish between these contributions and these fails. This is done for many other oxides. So, in the last actually few minutes I am going to discuss about instrumentations, what is done. So, what I have shown you in the nutshell is basically XPS as a technique and to be used for fingerprinting, like you can detect certain elements, electronic states of the element present very well, and also even we can distinguish between the spin orbital splitting of a particular orbital like 2p or 3p or even f, d orbitals, we can distinguish very clearly. I have done you that. Then we can use XPS to measure the compositions very well. I have shown you how it can be done. Finally, what last few 10-15 minutes I have shown you that XPS can actually use to determine the chemical shifts when some reactions happen with two species like metal and oxide, metal and nitride, or metal and nitride like cubic boron nitride. We can actually determine very precisely those states. Last thing, that is what I am going to discuss, the instrumentation. Instrumentation is very complex, let me tell you. In the XPS, the machine itself is very costly, it is about 4 to 5 crores, and very few laboratories in India possess this kind of instruments. What is the basically electron energy analyzer is? Basically, it's the heart of the instrument is basically electron energy analyzer. We have a X-ray source in this instrument, in this particular instrument, and if this X-rays falls on the sample, generates the photoelectrons, and these photoelectrons then are captured, or rather then are basically captured in a different manner, and then their energies are measured, and this is done by electron energy analyzer. The most important one is concentric hemispherical analyzer. Here you can see here, this is R1, R2, there are different concentric radius regions are used here, R0, R1, R2. R1 is basically negatively charged and R2 is also negatively charged but different, and there is a slit plate here, you can see W1 or W2 depending on that. The electrons actually moves in this and then get detected. So, for an electrons of energy E0 at S, the slit width, delta E by E0 is basically 0.63 by W1 by R0. W1 is basically the width at of this, I think this width, divided by R0 is this concentric cycle radius, concentric cycle, this is a radius or half diameter. So, this is the formula what can actually separate out different delta E values. So, if you have to have different delta E values, you have to either have different WI, W1 or R0s. So, that is why different R0s are shown here, one can actually vary the R0s. Second thing is that I discussed about this pass energies and transport lengths. You need to have very high resolutions in XPS because binding energies to be measured can differ by about 0.5 electron volts. So, that is why we require analyzer with W equal to 1 millimeter and r equal to 1.2 meters, you can understand, small width but large radius. That means it is convenient to retard the energy of the incoming electron, so that they have a lower energy as they pass through this analyzer. This is what is basically used in a pass energies. Lens system, which normally used in this in a particular system, it helps us retard the electron energy and also allows us to focus the electron energies from the sample to increase the throughput. So it retards the electron energy and also allows us to focus that, otherwise you cannot get it absorbed, it must be focused. So electrons can be focused very easily because they are charged particles, there is no problem. And there are other issues also. I am showing you this schematic picture which I obtained, but not very good, but it can be seen here. As you see, basically is nothing but this is present in Escalab MK2 analyzer. You have a metal vacuum vessel, sample is here, and the X-ray falls like this and gets transferred there, electrons, protoelectrons, and then there are different plates. There is a aperture here through which electron pass through. This is the inner hemisphere, this is the outer hemisphere, that is what I shown you just now, these two hemispheres here, inner and outer hemisphere, R1 and R2, and inside this electron moves and gets detected. This is a detector assembly, and this is the slit adjuster. There is a slit here, the slit means this slits, this can be adjusted using this adjuster, and that is how it is done. So what are the factors which are responsible for measuring the electron energy? Pass energy of this system, analyze the radius R1, R2, slit width W1, W2, elements in the transport lens, and energy of the photoelectrons. The transport lens, this is a transport lens. So there are a lot of elements which allow you to focus the electron so that it can pass through the aperture and falls and move inside this hemispherical region. Well, another important thing of the part of the instrument is the monochromator. X-ray monochromator is basically monochromatized X-ray. This is done by Bragg's law, as you see here. Bragg's law is in lambda 2 Lee sin theta. If you use aluminum, K alpha was 8.3 is the lambda, and if you use a quartz plates, D become this and theta is this. So by using different plates, different crystal plates, actually we can monochromatize, we can get exactly the same, only the aluminum K alpha and not any others, K beta or K alpha 2, we can do that. Lastly, the photoelectron spectra, this is actually the whole setup looks like, as you see here. You have an electron gun, electron beam falls, X-rays are generated, X-ray falls on the sample, okay, so X-ray falls on the crystal, that quartz crystal, monochromatic X-ray comes, it falls on a sample and then photoelectron generated and then measured in this. So this is basically the X-ray thing, and this is what is the photoelectron generator. Now one can actually get lots of things. Obviously one can get, this is silicon and carbon peaks, one can get Auger also here, but we are going to discuss separately about the Auger electrons. And I just want to finish it up using showing that if you show the pass energies, as you change the pass energy from 10 to 80 electron volts, what happens to the particular pieces like PET here, polyethylene tetrafluoride, which is used in the bottles. All these plastic bottles are actually made of this, and you can see C1s peaks, how it gets shifted, how it gets affected by this way. Finally, if you say about 80 kilo electron volt pass energies, we get a very nice the peak positions of the carbon 1s very easily. So with this I just close this discussion on the X-ray photoelectron spectroscopy. In the next class I am going to discuss about the Auger spectroscopy.